High-speed milling. Abstract. High-speed milling (HSM) has become a key technology in modern manufacturing, offering significant advantages in productivity, precision, and surface quality. This report provides an overview of the principles, benefits, challenges, and applications of HSM in industrial practices. It also highlights recent advancements and emerging trends in the field, aiming to provide valuable insights for both academic and industrial professionals. 1. Introduction. High-speed milling is a machining process characterized by high spindle speeds, feed rates, and cutting velocities. Compared to conventional milling, HSM allows for faster material removal, reduced cycle times, and superior surface finishes. This technology is widely adopted in industries such as aerospace, automotive, mold and die manufacturing, and medical device production. 2. Principles of high-speed milling. HSM operates on the principle of maintaining a high cutting speed to achieve minimal cutting forces and better chip evacuation. Key parameters include cutting speed, the speed at which the tool rotates, often exceeding 40,000 rpm. Feed rate, the speed of tool movement relative to the workpiece. Depth of cut, generally shallow to avoid excessive tool wear and heat generation. The process relies on advanced machinery with high spindle speeds, rigid structures, and precise control systems. 3. Advantages of high-speed milling. Increased productivity. Higher material removal rates result in shorter production times. Improved surface finish. Reduced tool vibrations and optimized cutting parameters enhance surface quality. Reduced heat generation. The high-speed cutting process minimizes heat transfer to the workpiece. Maintaining material integrity. Versatility. Effective for a wide range of materials, including hard-to-machine alloys. 4. Challenges in high-speed milling. Despite its benefits, HSM poses several challenges. Tool wear. High cutting speeds accelerate tool wear, requiring advanced coatings and materials. Machine stability. High spindle speeds demand rigid and vibration-resistant machines. Cost. The initial investment in HSM equipment is significant. Complexity. Requires skilled operators and advanced software for optimal performance. 5. Applications. Aerospace industry. For lightweight and high-strength components in aluminum, titanium, and composites. Automotive industry. For rapid prototyping and machining of engine parts. Mold and die industry. For intricate geometries and fine surface finishes. Medical devices. For precise and biocompatible implants and tools. 6. Recent advancements. Recent research and technological developments have focused on tool materials, Advanced coatings such as diamond-like carbon (DLC) and cubic boron nitride (CBN). Machine design. Improved spindle designs, thermal stability, and vibration damping. Process optimization. Real-time monitoring and adaptive control systems to enhance efficiency. Hybrid techniques, combining HSM with other processes like additive manufacturing for greater flexibility. 7. Product quality in high-speed milling. When conducting high-speed milling processes, product quality is a crucial factor in ensuring accuracy, surface finish, and mechanical properties of the machined part. Below are some factors influencing product quality in high-speed milling. Accuracy. High-speed milling allows for achieving high precision in machining parts. Controlling cutting parameters such as cutting speed, depth of cut, and feed rate is crucial for product accuracy. Surface finish. High-speed milling often results in better surface finish compared to traditional milling methods. Choosing the right cutting tools, controlling cutting temperatures, and applying effective cooling methods play significant roles in achieving the desired surface finish. Tool durability. High cutting speeds in high-speed milling can pose challenges to tool durability. Proper selection and application of cutting tools, as well as efficient cooling systems, can increase tool durability and maintain product quality. Vibration control. Vibration can affect product quality in high-speed milling. Temperature control. High cutting temperatures are common issues in high-speed milling. Using effective cooling systems and tools with good heat dissipation capabilities help control cutting temperatures and enhance product quality. Machine stability. Machine stability also influences product quality. 8. Conclusion. High-speed milling represents a transformative approach in modern manufacturing. Its ability to improve productivity and precision makes it an invaluable tool in high-tech industries. However, addressing challenges such as tool wear and high investment costs is essential for broader adoption. Ongoing innovations and research will continue to expand its capabilities, ensuring its relevance in future manufacturing systems.